right. Excuse me. Let's see. Today I was going to say a couple of things to finish up the discussion of Bayesian inference. We were talking about that on Friday, and I was going to revisit the exact same example we were playing with, which was the billiards example, where we're going to play somebody who we don't know and have not played before, and we're not confident in our abilities. So we're going into the interaction with prior beliefs about our abilities in this game. And then we're going to play a few games, and at the end, after playing those games and observing a win-loss record, we're going to update our beliefs. Bayesian thinking and Bayesian inference enables you to have prior beliefs that you then incorporate with observed data to update your beliefs. Okay, so we started on Friday. Let me just say what we're going to do today. Let me finish that statement. We're going to see this one more time and a couple of extra features of Bayesian inference. And then we're going to start talking about linear regression. And we'll spend a couple of weeks on regression modeling, because regression is often the way that we end up analyzing data anyway. A lot of what we do in statistics can be formulated as a regression problem. So with the billiards data, what we did on Friday was, at least initially, allowed for the value of P being the parameter that's probability we win any given game with this opponent. P is the unknown parameter. And what we do with Bayesian thinking is we assume a prior distribution for the parameter. And remember, that's a little different from the way, like a frequentist approach of statistics, which is what we do with traditional confidence intervals and p-values. That's a frequentist approach. Bayesian approach is different in that we allow the parameter or parameters to be random and have their own distribution. We started out by making this a pretty simple problem. Namely, we're going to allow for P to only take 11 possible values. So P is a number between 0 and 1. It's a probability. So strictly speaking, it could be any number between 0 and 1. But to illustrate things, we just initially said, let's only think that P can be 0 or 0.1 or 0.2 up to 1.0. So I'll run this stuff again. Here are the possible values of P. Possible values of P. And here was our prior. So I just made these numbers up, but a separate probability for each of the possible values of P. And most of the probability is over towards the left for lower values of P, reflecting our low confidence in our ability to play billiards. Okay, so then assume we observe some actual data. We play 3 games, and we win all 3. So the way that we represent this new information that we observed is with a likelihood. We say there's some distribution that governs what we observe. If I'm playing a game and I could win or lose, if we treat every game as independent of the other, which may or may not be reasonable here, and if we assume that the probability that I win is constant for every single game, which again may not be a reasonable assumption, but if we assume those things, then our win-win-win is the result of 3 Bernoulli trials. Bernoulli's success-fail trial. We can think of it as 0 or 1. And the probability, if you were to do 3 Bernoulli trials independent of one another, each of them have the same probability of success, the probability of win-win-win is this right here that we're calling a likelihood. P to the third, because there were 3 successes, 1 minus p to the 0, because there were no failures that we observed. So this right here is itself a vector, because p is a vector. The likelihood we think of as a function of the parameter. We have, therefore, a separate likelihood calculation for every possible choice of p that we're considering. The likelihood of seeing 3 wins in a row, if p was really 0.1, is 0.001. So our data are not consistent with this choice of p, but it is consistent with these higher levels of p. One thing real quick, this is not a probability distribution, by the way. A likelihood is a function of p. So for different choices of p, we're not asking what's the probability of p. These are asking what's the probability of seeing your data if I tell you these different choices of p. So in particular, those don't sum to 1. Okay, and then the posterior is an application of Bayes' theorem. So the posterior is the probability distribution of your parameter given the data you saw. So Bayesian thinking, Bayesian inference on a parameter p. We need a prior distribution, call it f sub p maybe, and we need observed data that we use to compute a likelihood. We'll call this capital L of p, a function of p. And once we have both of those, we can apply Bayes' theorem to get posterior. The posterior, let's call it G P. Posterior GP evaluated at P is the likelihood, which we can think of as probability of seeing our data given the choice of P, times the prior for P, and divide by or integrate in the continuous case. We'll divide because we're treating P as discrete. Sum over all P of that thing in the numerator. Another way to write that is that we have product of likelihood prior divided by this constant that's in the denominator. We can think of this as the sum over all P of probability of the data given P times prior probability for P. Another way to write that is sum over all P, probability of P and observing the data we saw. So a conditional times a marginal, data given P times the probability of P, gives you a joint probability. Definition of conditional is joint divided by marginal. So conditional times marginal is what's in the denominator. If you sum over all the p of joint probabilities, think back to STAT645 if you had p, let's do it like this. Here's a sample space for p. Sample space for p. And each one of these little slices represents the different possible values that we're considering for p. I probably don't have the numbers completely right there. I probably don't have as many slices as we need. But suppose we had 11 slices. Then given our data, we observed we observed data. So what we're doing in this calculation back on the slide above us, think of our data as having probabilities under each of these slices. I'm just going to draw a arbitrary region, and let's call that, let me do a different color. Let's call this region A. Just call it something, A. The probability of A is the probability of A intersect with the region P1. So I'm going to call this region P1, P2, P3. We had 11 of them. The probability of A, marginal probability, is the probability of A and P1 plus the probability of A and P2 plus ... A and P11. So it equals the sum over all P of probability A and P. That right there, that slide is an illustration of what's called the law of total probability. Probability of any event A is the same thing as probability that probability right there plus that probability right there and that one and so on. That's all it is. You're adding up all those little overlaps. So this that we're working on up in the top right, that summation, same thing as probability of our data. So I could put down in the denominator here a marginal probability of our observed data. So like averaging over all choices of P, what's the distribution of our data? Big picture at this point, we had prior, we had likelihood, and now we have posterior. Posterior is now our updated beliefs about the values, the likely values of P, having incorporated our data. That's what we're doing right here. The posterior is likelihood times prior divided by the sum of likelihood times prior over all possible values of your parameter P. So if we compute this, we have a vector, one element for every of the possible P's that we are considering. There's 11 elements there. And these are the updated beliefs. Compare them to the prior beliefs, they have changed. In particular, they have shifted a lot of the probability mass over to bigger values of P. So we had this picture. Prior is red, current posterior is blue. Okay, and then we saw now what happens if we play another couple of games, and let's say we lose the next 2 games. We can do one of 2 things to update our beliefs yet again. One is to treat, at this point, having played 3 games, treat it like our prior beliefs now are the posterior beliefs from just a moment ago. Now that we have played the 3 games, my beliefs are reflected by that posterior we just computed. And then we could apply Bayes' rule again to incorporate these 2 new games. In this case, the likelihood I want to fold into the posterior calculation only is for those 2 losses. So the likelihood at this point is p to the 0, 1 minus p to the 2. We then apply the same idea, likelihood times prior divided by the sum of the likelihood times prior. That's one way. That's kind of a sequential way in the sense that you started with some beliefs, observed some data, updated your beliefs. Then new data came in, and you incorporated it on top of what you already had. An equivalent way to do that is to go back to your original prior beliefs and treat it now as if you've played 5 games, 3 wins followed by 2 losses. This likelihood has all 5 games in it, p to the 3 times 1 minus p to the 2. Then the posterior is that likelihood times the original prior divided by sum of likelihood times prior. They both give you the exact same result. That sequential element, that sequential type of analysis is handy, and it's widely used in, for example, clinical trials and things like that, where you're obtaining data over time. And you need to be monitoring the data for evidence of adverse events or reasons for concern that you need to maybe stop the trial or something. So now let me show you the end of this script, which made it a little more sophisticated. So p, unknown parameter, it's a probability. It's a number between 0 and 1, and it could be any number between 0 and 1. So to be more flexible, we would allow p to take any number between 0 and 1, in which case we would not be able to do a prior like this one, because we can't enumerate all the possible values of a real number between 2 endpoints. What we can do instead is choose a continuous distribution to use as the prior. One possibility is the beta distribution. That would make sense because the beta is appropriate for random variables between 0 and 1. So if we were going to consider a beta distribution, the beta has 2 parameters, a scale and it has 2 parameters. Call it alpha and beta. We would like to pick an alpha and beta that reflects roughly our prior beliefs. And so we might play around with different choices. One choice would be beta 1, 1. That's the same thing as the uniform distribution between 0 and 1. So that would be maybe something we'd want to do if we wanted to be just let the data decide about p, what the value of p is. If I didn't want to impose any beliefs prior to seeing the data, we could give what's called a non-informative prior. A uniform prior gives equal probability to every possible p. So we're not kind of biasing our beliefs. We're going to let the data tell us exactly. We ended up looking at this one, beta 1.8, 6, because it kind of looks like the prior that we were working with. A lot of probability over at the left. Okay, so this is this right here is the result of a little bit of math. It turns out that if we had, like in our case, we have data that is binomial. So let's say that x, after we play our 5 games, let's say that x, capital X, is the number of wins out of those 5 games. Then we can say x is binomial. Binomial is just if you do n independent Bernoulli trials, we did 5 of them, each of which had the probability p of success, and if you count up the number of successes out of those n trials, that's a binomial random variable. If we say x is binomial, and we say p has a prior distribution that is beta, then it turns out analytically that the posterior distribution, p given x, is also beta. And the terms or the coefficients, parameters, are like what's written here. If you have a beta likelihood, a binomial likelihood and a beta prior, then the posterior, apply Bayes' rule and work out the math, you get back another beta distribution. Its parameters are your prior alpha plus how many wins you observed, and your prior beta plus the number of trials minus the number of wins. That's where we had this version of the posterior. After winning 3 games out of 5 trials, the posterior beta has parameter alpha, 1.8, plus 3, so 4.8. And it has second parameter equal to prior beta plus 5 minus 3. So 6 plus 5 minus 3 is 8. That means now that we have derived the posterior distribution as a continuous distribution, blue curve. That's nice because now you could estimate probabilities straightforwardly by integrating this known function. Sometimes when you do Bayesian inference, you have this nice result where the posterior distribution is a known quantity, beta or normal or something like that. When you can do that, Bayesian inference is a snap. All you have to do is, for example, get the inner 95% of this posterior distribution, and that's what we call a credible interval. Or compute the expected value of the posterior distribution. That's another common summary. What's the posterior mean, for example? Okay. This is new. I added this morning, but I wanted to show how, that result, you're just taking my word for it at this point, that the beta, binomial beta, gives you back a beta posterior. So you could look that up in a stat book. You could also compute it manually. If you didn't know, in many cases you don't have that kind of relationship. That's called a conjugate relationship. When a likelihood combined with a particular prior gives back another distribution of the same family as your prior, then the likelihood and prior are said to be conjugate to one another. Normal is conjugate with normal, for example. Binomial, conjugate with beta. Poisson is conjugate with gamma. So whenever you can do that, it's great because you know analytically your posterior distribution. Often, in more sophisticated real-world analyses, we don't have that because there's no analytical expression for what the posterior is. In cases like that, you can computationally figure out the answer. So what I'm going to do here is pretend we didn't know that result about beta binomial. I'm going to allow for a bunch of possible values of p, from 0.01 up to 0.99. Let's allow for 1,000 different values. Let's treat the prior as the one that we mentioned up above. So evaluate the beta density, PDF. D beta is PDF of the beta. Evaluated at all of our p seek values. And then we could compute a likelihood. After 5 games, we won 3. So evaluate the binomial PMF, probability function, D binom, for 3 successes out of 5 trials, and we evaluate it for all those possible values of p. In order to apply Bayes' theorem, we do likelihood times prior divided by, in the discrete case, the sum of likelihood times prior. In the continuous case, this denominator here, if we treat p as continuous, then this summation needs to be an integral because p is a real number. So what I'm doing here is likelihood times prior, just like we've done above, and what goes in the denominator I'm going to compute on the previous line. So there is an integrate function in R that does numerical integration. What I need in that denominator is the integral of likelihood times prior, where we integrate over all the values of p. I'm not using any knowledge of a conjugate relationship here. I'm just saying I know in the denominator I need what's in the numerator integrated over all p's. So here is integrate, and then I defined a custom function. This is not critical that you know how to do this for the purposes of this class. But this is saying integrate the function of p, a function of p, that's defined as likelihood times prior. Integrate from 0 up to 1, because that's the region of possible values for p. That will give us back the constant that goes in the denominator, and then we can compute the posterior. Here's a picture that just illustrates that this gave us back the same posterior that we would have gotten if we had used the conjugate relationship. On this picture, the red curve is the prior. The blue thick curve is the one we just computed with R. No knowledge of conjugates necessary. And then the reason it's kind of fuzzy is because I overlaid a dashed white line at the expression that we know is true from the conjugate relationship. So this picture is just showing that the conjugate relationship holds, basically, and that you could have gotten the same answer even if you didn't have a conjugate relationship. So think of this as like a general way for an arbitrary prior distribution. Even if I didn't have beta in here, if I chose some other distribution and that didn't give me this conjugate relationship, I could still do Bayesian inference with numerical methods, numerically integrating. Okay, so now let me just make a couple of comments about what we might do with a posterior distribution. We have this distribution for the parameter given the data we observed. What kind of inference do you do from a Bayesian perspective? One that I've mentioned before is what's called a credible interval. It's analogous to a confidence interval. It's an interval estimate of p, but it comes from the posterior distribution. So it's just like in the frequentist case where you go to the sampling distribution of your statistic, and if you get the inner 95% of that, you get what's called a confidence interval, 95% confidence interval. If you do that same trick with a posterior distribution, We call it a different thing because it is a different quantity. It has a different interpretation, but it is still, in some sense, an interval about which we can be 95% confident. What's nice about having done this from a Bayesian framework is that this interval right here, we get to interpret as the probability that p is between 0.143 and 0.644 is 0.95. None of that 95% of all intervals constructed this way will contain the truth. Because of the way we're using probability, we can say the probability that p is in there is 0.95. Another common summary to compute in a Bayesian approach with a posterior distribution is a posterior mean. Given the data, what is the mean of the distribution for p? I have here another integrate instance. So integrate the function of p, an expected value, if you recall, so if x is a continuous random variable, with probability density function f, say f theta, the expected value of x, it's like an average, but it's a weighted average where possibilities are weighted by the PDF. So more common choices of x are weighted more heavily than less common choices. What it looks like mathematically is an integral of possibility times, roughly, probability. A straight average of n numbers would be 1 over n add up the x's. Same thing as add up xi times 1 over n. A straight average, a simple arithmetic average, is adding up all the possibilities and weighting each of them by the same number. Everybody gets the same weight. An expected value, it's a similar idea, add up possibilities and weight them with something, but we allow for different possibilities to have different weights. To compute an expected value, I then need to integrate possibility times probability. So here is posterior expected value, 0.375. Looking at the picture, we have an integral or an interval from 0.14 up to 0.64. So right around here up to right around there, which makes sense. That's right where the bulk of the distribution is. And posterior mean, the expected value of that blue distribution, is right around in here. Okay, I think that's the extent to which we're going to talk about Bayesian stuff in this class. There is an entire class that our department offers on Bayesian Inference, in case you're interested. All right. So let's move on. Let's start talking about regression. Let's start with the simplest regression model. What is regression about? Regression is a way to relate a response variable, a variable that is the focus of your attention. Relate that to a predictor variable or a collection of predictor variables. In this case, the simple linear regression model has a numerical response, call it y, and one numerical predictor, in this case, or yeah, call it x. The linear regression model is written this way. We say that the ith observation of the response for individual I, is equal to beta 0, a y-intercept, plus beta 1, a slope, times xi, plus some random error. What we would actually observe is on the right panel there, with x on the horizontal axis and y on the vertical axis, all those dots they're representing a sample. We have in mind a linear relationship between y and x. As x changes, we expect y to change according to this linear relationship. What we observe in practice is the scatter plot on the right, all those dots. Our model says that underlying that scatter plot is a line. This line we define in terms of the mean of y. You can see with your eyes that y does not exactly follow a linear relationship. We're not doing a deterministic problem. We think that on average, y tends to follow x in a linear way. The line that's drawn through the scatter plot is then beta 0 plus beta 1x. And that is the mean of y. These random errors, these epsilons, are treated as IID, independent and identically distributed. Classically, we'll say normal, but we have ways around that. But definitely mean 0. The random error is bobbing around 0. The line is what describes the relationship on average. But if you were to go to any one particular value of x, call it x0, and sample there, go find a bunch of individuals with x equal that value of x, x0, and take a sample of 20 individuals, say. What you would see is a distribution about the line. The average response when x is x0 is whatever the line is when x is x0, that red dot. But because we're doing statistics and sampling from a population, we won't repeatedly see that red dot every time we get somebody with x0. We're going to see things bobbing around that line. That's what I mean by this curve that I've drawn on top of the line. If you were to go to any one spot x0 and sample individuals that have that value for the predictor, you would see, according to our model, a normally distributed collection centered at the line. Another thing that we have about these epsilons, they are all independent. That's important, and we're going to have to do something about that when we get to correlated data. Longitudinal data, for example, we have multiple measurements over time on the same individual, so these epsilons will not be independent anymore. We'll have to do some specialized stuff. But the classical linear model assumes everybody's independent. These errors have mean 0 by construction, and they have a common variance sigma squared. If you look back at that curve on the line when x is x0, the model says that's a normal curve and it has variance sigma squared. That sigma squared, according to the model we have on the screen right now, is expected to hold for all possible choices of x. So if you imagine picking up x0 and sliding it down and up the horizontal axis, as you slide x0, the red dot is going to slide along with it to indicate the mean. And this bell-shaped curve is also going to slide up and down the line, but it's not going to change in shape. There's constant variance across all values of x is one assumption. It's the default assumption of a linear model. We will figure out ways to get around that. Because suppose you had this scatter plot and there's less variance maybe at the low end than there is at the high end. That's not an uncommon phenomenon. If that were the case, this model is insufficient because it is assuming everybody's independent and the variance, the residual variance is the same, regardless of the predictor value. According to this model, this is a probability model. We have in mind x's and y's that we could observe from the population. And we're specifying a probability model. Another way to think of that is we're specifying a likelihood. The reason we can say that we're doing that is because we stated something. Here's a parametric relationship between y and x. There's two parameters here that we need to know. And then there is uncertainty in the form of these epsilons, and we gave them a named distribution. Okay, so we have a model. We can, in terms of our model, interpret the regression coefficients. What do they mean? Beta 0 and beta 1 are like an intercept and a slope, respectively. So beta 0 you would interpret, if we just had a line, y equal beta 0 plus beta 1x, we would say beta 0 is what the line equals when x is 0. And similarly, beta 1, you would say it's a slope, so it's like rise over run. It's the change in y for every 1 unit increase in x. But because we're working with a probability model like this, we don't expect that there is a deterministic relationship between y and x. Rather, there's a stochastic one. So beta 0 and beta 1, while roughly they are intercept and slope, what they specifically mean has to do with expected values. In particular, beta 0 is the expected value of y when x equals 0. If we're looking at this line, this relationship, if you plug in x equals 0, what the model says is you're going to observe y's that equal beta 0 plus random error. If you were to sample a bunch of individuals that had x equals 0, you would not repeatedly get beta 0. You would get beta 0 plus random sampling error. So beta 0 is not strictly the value of y when x equals 0. More specifically, it is the mean of y when x equals 0. And similarly, the slope, beta 1, is a mean difference. The mean difference in y when x is incremented by 1. Expected value of y when x is 1 minus expected value of y when x equals 0, for example. This would hold, interpretation would hold for any value of x and it minus 1. Same slope holds all up and down the line. Okay, so regression primarily is, at least it's initially presented in your Stat 101 class, for example, as we have a numerical response and we have one numerical predictor. Might be weight versus height. We want to model weight as a function of height. What we're going to see is that this can be generalized in a lot of different ways. For example, suppose x is not a numerical variable, but rather a categorical one. We can still do regression modeling. And in fact, it's equivalent to things like t-tests and ANOVA. Both of those are regression. Suppose we had income and x is degree type. So did you major in the arts or in the sciences, say? I'm defining x, the predictor, to be 0 for arts, 1 for sciences. I can write down a regression model, a linear regression model, even though x is not a continuous number, and it doesn't really make sense to draw a line with x just taking two values. There's nothing wrong with this as a statistical model or probabilistic model. We can say that the mean of y when x equals 0 is beta 0. And the mean of y when x equals 1 is beta 0 plus beta 1. Let me write that down for us real quick here. So the simple linear regression model let's say y is continuous and x is binary. Then the model is yi equal beta 0 plus beta 1 xi plus epsilon I. And those epsilons are IID. Okay. So according to the model, the expected value of y when x equals 0 is beta 0. So that it would actually be beta 0 plus beta 1 times 0 plus the expected value of epsilon. And the epsilons have mean 0. So we get back that the mean is just beta 0. Similarly, the expected value of y when x equals 1 would be beta 0 plus beta 1. You plug in x equal to 1, that gives you beta 0 plus beta 1 plus epsilon. The expected value of any epsilon is 0. Then because of these relationships, we can say beta 1 is the difference between those two expected values. If the expected value when x is 0 is beta 0, and the expected value of y when x is 1 is beta 0 plus beta 1, beta 1 is the difference in means. So the difference between the mean when x equals 1 and the mean when x equals 0. So suppose we had data like income and degree type. Income is the response. We're interested in doing inference on mean income in terms of degree type. If I wanted to ask, is there a difference in mean income by degree? If we wanted to do inference, yes or no, is there a difference in mean income? We could do a t-test, but equivalently, we could ask, is beta 1 equal to 0? Because beta 1 is the mean difference. It's the mean when x is 1 minus the mean when x is 0. That is the parameter of interest in this case if I want to ask, is there a difference? The null hypothesis that that corresponds to for this linear model is that beta 1 equals 0. This is equivalent to, say, a two-sample t-test where we ask, is the mean in the arts group equal to the mean in the sciences group? Yes or no? All right, we're out of time. We're going to kind of take that baby steps to build on what we know with regression, and we'll see lots of uses of it with example data sets starting Wednesday. Okay? See ya.